Imagine a machine weighing 13,000 tons, capable of moving 400 cubic yards of material in one scoop. This is the walking dragline, the undisputed heavyweight champion of earth-moving. Its deployment is dictated by the stripping ratio, the critical economic metric defining the viability of surface mining. This ratio measures the volume of waste rock, or overburden, that must be removed to access a unit of recoverable ore. If the ratio exceeds the economic threshold, typically ranging from 10-to-1 to 15-to-1, depending on the commodity and market price, the mine becomes unprofitable. Draglines are deployed specifically to manage massive overburden volumes efficiently, ensuring the mine stays below this critical ratio. They achieve the lowest cost per ton moved in high-volume strip mining operations globally, operating continuously for decades. Their immense reach allows them to cast spoil directly into previously mined pits, minimizing rehandling costs and maximizing efficiency in large-scale coal and oil sands extraction. The dragline does not use wheels or tracks. It walks using massive hydraulic or mechanical feet, lifting its entire tub base and stepping forward typically 6 to 8 feet per cycle. This walking mechanism distributes the immense static and dynamic loads over a large surface area, preventing ground failure in soft overburden. Structurally, the machine consists of the revolving frame, the tub, and the boom. Booms can extend over 300 feet, constructed from high-strength tubular steel lattice to minimize weight while maximizing reach. The bucket is attached via hoist ropes and the critical drag chain, which pulls the bucket horizontally across the bench face. The largest buckets can hold over 150 tons of material. The tub provides the stable foundation and houses the massive swing rack gear, which facilitates the 360-degree rotation of the revolving frame. Draglines are exclusively powered by high-voltage alternating current electricity, typically requiring a dedicated substation connection ranging from 7.2 kilovolts to 35 kilovolts. The power demand is enormous, peaking at over 20 megawatts during the hoist and drag phases. To manage these massive, fluctuating loads and provide precise speed control for the main motors, older machines utilized motor generator sets, converting AC input to DC power for the drive motors. Modern draglines employ solid-state power electronics, specifically cycloconverters or insulated gate bipolar transistor drives. These systems offer superior energy efficiency, regenerative braking capability, and reduced maintenance compared to the legacy MG sets, directly lowering the operational expenditure related to electricity consumption. The regenerative braking captures energy during the lowering phase of the bucket, feeding it back into the grid. The standard dragline cycle involves 4 phases: digging, hoisting, swinging, and dumping. Cycle time is the primary metric for operational efficiency, ideally maintained between 45 and 60 seconds. Digging depth and swing angle are the key variables impacting this time. Operators strive for minimum swing angle, often less than 90 degrees, to reduce inertia and maximize cycles per hour. Advanced monitoring systems track bucket fill factor, swing velocity, and power consumption in real time. Optimization software uses this data to provide immediate feedback to the operator, ensuring consistent performance and minimizing non-productive time, such as excessive repositioning or unnecessary deep digging. Maintaining a high bucket fill factor, often exceeding 95%, is crucial for achieving the lowest cost per cubic yard moved.
The initial capital expenditure for a large walking dragline can exceed $100 million, making it one of the largest single-asset purchases in the mining sector. However, this massive upfront cost is amortized over a service life often exceeding 40 years. The financial justification relies on the machine's low operating cost per bank cubic yard moved, which typically falls below $1. Operating expenditure is dominated by electricity consumption, maintenance parts, and labor. Depreciation schedules are critical. Accelerated depreciation methods are often used to reflect the rapid initial wear and tear and the high cost of major component replacements, such as boom repairs or tub refurbishment, which occur every 15 to 20 years. The long lifespan necessitates robust financial planning for major capital renewal projects. Maintenance is a critical path item. Unscheduled downtime can cost a mine hundreds of thousands of dollars per hour in lost production. Planned outages, known as shutdowns, are scheduled annually or semi-annually for major inspections and component replacement. Rope management is paramount. The hoist and drag ropes made of specialized steel wire require frequent inspection and replacement, costing tens of thousands of dollars per set. The largest maintenance expense involves the replacement of the massive swing rack and pinion gears, which guide the revolving frame. Predictive maintenance strategies, utilizing vibration analysis and oil sampling, are essential to anticipate component failure and convert unscheduled downtime into manageable planned maintenance events. Specialized rigging crews are required for boom maintenance due to the extreme height and structural complexity. The global market for new draglines is highly concentrated, dominated primarily by Komatsu Mining, which acquired P&H, and Caterpillar, which acquired Bucyrus International. These manufacturers compete on reliability, cycle time, and technological integration. The primary demand drivers are large-scale thermal coal mines in regions like Australia, India, and the United States, and increasingly oil sands operations in Canada. Due to the immense logistical challenges and cost of relocation, draglines are typically assembled on-site and remain there for their entire operational life. The secondary market for used draglines is extremely limited, often involving only the sale of major components or the relocation of smaller units within the same geographical region. Manufacturer support contracts are essential due to the proprietary nature of the electrical and mechanical systems. Regulatory compliance mandates strict environmental controls, particularly concerning land reclamation. Draglines facilitate concurrent reclamation by immediately backfilling the mined-out pit with overburden, minimizing the area of disturbed land at any given time. Noise pollution is a significant concern in proximity to residential areas, requiring specialized acoustic dampening on the machinery house. Dust suppression is managed through water sprays applied to the digging face and spoil pile. Furthermore, legal requirements often dictate the maximum allowable vibration transmitted through the ground during walking and dumping cycles, necessitating precise operational protocols to prevent damage to nearby infrastructure or geological instability. Failure to adhere to reclamation schedules can result in substantial regulatory fines and permit revocation. The future of dragline operation centers on automation and remote control. Fully autonomous draglines are currently in development, aiming to eliminate human error and allow continuous operation in hazardous environments. Remote operation centers, often hundreds of miles away, allow highly skilled technicians to manage multiple machines simultaneously, optimizing efficiency across an entire fleet. Predictive maintenance, leveraging industrial Internet of Things sensors, monitors thousands of data points on motors, bearings, and structural stress. This data is analyzed by machine learning algorithms to forecast component failure with high accuracy, maximizing uptime and reducing the reliance on fixed maintenance schedules. This shift minimizes labor costs and improves safety by removing personnel from the immediate operational zone.